Yes, hi. Good afternoon, everyone. I hope the coffee was good. I'll try to entertain you for the 20-25 minutes. I'll try to catch up. I have a lot of slides. I did change them during the day while listening here at the presentation and understanding what is the audience expertise. And I understood that most of you are programmers and you are dealing with programming multicores, many cores, even more than many cores. And this is why I just replaced a significant amount of my original slides with some code examples, because I would like to show you that these devices that you probably have heard about, the FPGAs, that I'm not going to even mention in my talk, that's the first and the last time I'm naming this, could be programmable. So, do we use these devices? Yes, we do use these devices in the company. So basically our technology is based on those silicon devices simply because there is no other choice. So there is no technology that allows us to program and instantiate a massive scale static data flow graphs directly on the silicon. And these are the only devices available that allow us to do so. Are we co-guilty for Amazon deploying them on the cloud already a year ago? Yes, we are. We did collaborate and they listened to our experience that is 14 years of building systems based on those devices. And now we have them on the cloud, and the real question is how we program all of this, how we get the performance out of the systems. So this is what I'm trying to cover. So the motivation is, see, we all know, we knew the single cores, then we started using the silicon area by dividing it and putting more cores, and even some group at UC Davis developed the KiloCore processor, which is shown here, right? Like a lot of small, tiny processors with only 72 RISC instructions doing 16-bit arithmetic. Oh no, 14-bit multiply other. Excellent. And there is some interesting thing. They have some FIFO buffers as part of each of these small processors. So the number of processors become larger and larger, and the functionality that you have there becomes tinier and tinier. So which means, what about we do not even break down the processor down to the basic transistor, build some simple arithmetic operations, interconnect them the way the application and the data set that we process requires, and do the job. So this is the ultimate custom computing implementation. And of course it should be reprogrammable because you want to run on the same system different workloads. You want to accelerate different algorithms. You want to accelerate different data sets. And this is what we claim, that here on that side of the spectrum should not be more and more tinier and tinier processors that you have to each microprogram and also synchronize, but really go for a sea of arithmetic units, memory, and interconnect wires that you can program as convenient as you can program and debug any program. Oh, let me see if I can convince you that this can be done. Conceptually, this is what shows the difference between programming a conventional processor, being GPU, CPU, multicore, whatever it is, and what we basically push for. You have a generic device and you put a different recipe in and different product comes out of it. For instance, you have a baking equipment and you can bake a nice dinner, you can bake a cake, you can bake something different. If you bake a lot of cookies, yeah, you can use the same generic equipment, but then you need a lot of time and a lot of experts to do the same thing. A better approach is to go into mass production, build the factory that can do very efficiently cookies. Another example could be the car manufacturing production lines, that you do not have a lot of specialists that can build every single piece of the car, but you have the production pipeline with specialists at each stage of the production pipeline, and then by having a lot of cars in partial production, you can achieve the throughput of actually letting a new car roll out of the door every few minutes. And that's how we want to treat the data. We want to build the factory to do this massive data processing, and of course, for a fixed algorithm. The algorithm should be fixed, but many of these algorithms, like climate modeling, geoseismic exploration, they are algorithms that everybody agrees what the mathematics is. There is only a lot of data that has to be processed. And that's basically what we try to do. Build the production, data production, massive pipeline, and then just let your data roll through. And ideally, a very good example, CG, conjugate gradient, is again an algorithm everybody agrees that it's very useful. If I would be able to just create the hardware structure that implements all of the different stages of the algorithm, and I have to do a massive amount of CG solvers, then I just have to stream my data, systolically clock these hardware modules that does only CG, and then be able to reach the one data element that is produced and consumed, obviously, at each clock tick of that specific hardware. So how we do that? Again, a little bit different as compared to programming conventional systems. Typically, we would start with a problem, we pick an algorithm that lets us solve the problem, then we pick a language we like, and I just heard that there are even languages slower than Java, and I'm amazed, but apparently they are. And then you just compile it to a certain architecture. You like ARM, you compile it for ARM, you use the compiler. Or you like Intel, then you compile it for Intel. But then where you run it on could be a processor for AMD that basically has the same architecture, but is, of course, a different implementation. All of these abstraction layers are very nice. They let us build very complex computers. However, as you can imagine, at each of these layers, we lose efficiency. When you lose efficiency, obviously, custom acceleration will be a problem. And then, obviously, we have to create this cross-layer solution that picks the right choices at each of these levels and creates this hardware accelerator for that specific problem that lets the basic solution being instantiated on the surface of the chip. Nothing new. For the ones that are a little bit older and old like me, we remember the time when Dan Slotnick was building parallel computers in Illinois, and he was saying, very rightly so, that in order to build efficient parallel system, you have to do both things, not one, not the other, both at the same time. Understanding your numerics, understanding what I am computing, why am I computing it, is what I'm computing the best way of doing that. But also the data management, what I do in each side of my system, how expensive it is to move a certain part of my data from one point to another point. And if you do not do both at the same time, this is never going to help you to build efficiently running. And this is bad now. I don't know why this stopped working. The Google Calendar. Excellent. Thank you very much. So there is a reminder that I have a call that I'm not going to be attending. Now let me find the window where am I back? I'm back. Good. So, as I said, there are multiple levels, and on each of these levels you have to take the right decision to implement the right solution for the specific algorithm that you want to accelerate and for the specific data set that you want to process. So, seems like very complicated. Now, on one side it's complicated, on the other side it is simple. Because if we compare how we program conventional processors, we have to take care for both things, right? The data management, where is my data, what do I do with my data, should I move the computation close to the data or the data close to the computation? That's fine, but I also have to take care of the efficient instruction sequences management and synchronization. Here, once I have built this vertical, massive mega accelerator, the only thing I have to do is just take care of the data movement. I have to fill this mass production data pipeline with the right data. Because if I build this pipeline and I build one car, right, I'm not very efficiently using my investment. I have to really keep it occupied at each clock cycle. Then this makes it indeed somehow simple. Would there be always normal CPU? Of course, because you have to run the operating system. You need a part of your system that deals with highly irregular control flow dominated tasks, also like interrupts. We cannot do that on the data flow accelerating part of the system. So there is always these two subparts, and then your algorithm works in parallel on both sides, and which is good news because we said, here we would like to build a very massive data production pipeline, which means my latency is huge, so which is an opportunity to hide the latency of data transfer between these two subsystems, which is good. We built our own hardware. We call them DataFlow Engines to not scare people, because when we say you have to program FPGAs, they run away the next minute. And we have the largest FPGA, unfortunately, in the middle, and a lot of memory, like 48 or 96 gig if you put a double density memory here. We abstract the memory in a different way. There is certain amount of fast memory included in the chip, and everything else is a large memory, which is just a large capacity, high bandwidth memory. Latency is not very critical because, as I said, the production pipeline that we build is like thousands or tens of thousands of pipeline stages. You cannot do that with any other technology. And then this is a good opportunity to hide latencies of interconnect. But anyway, as I said earlier, the latest generation card also influenced quite a lot what Amazon deployed on the F1, on the EC cloud as F1 instances, which means now you can write code for our accelerators, and then you can also target this code for the instances that Amazon lets you rent. And these are the properties, but the concept is the same. It's just different chip. If you paid attention, this is a Xilinx chip, and the previous generation card was based on Altera, that is now Intel. So we are completely agnostic. Our toolchain and approach work on any technology that allows us to implement static data flow graphs that are executed systolically. So I'm gonna skip a few slides. Let me show you a few examples. This is how the code looks like. I have some streaming input and streaming output. These are like long vectors of a specific data type, integer in this case, and specific size, 11 bits. I have the ability to control the data type and the size up to the bit level, because this FPGA devices allows us to configure the data paths down to a single bit, which means all the data paths shown here, because writing this code results in generating such a graph. They will be of 11 bits, and of course they will grow a little bit further. There's going to be a constant, and this is how it is. Is it difficult? Of course not. Then you can even implement choices. If your algorithm at certain level has some condition, and then you don't know should you take this branch or not, as what you should do in a conventional program. Here you just do both. I can write a conditional expression that implements the truth and the false part of my statement, and both of them will be instantiated on the surface of the chip. And then later on, when the results are available, the condition resolution, the output of the condition, will arbitrate the right output to the next stage of my data flow graph. Oh, okay, this sounds wasteful, but it sounds like, okay, I completely got rid of the branches, which is something that I like. What do you need? You just need this technology that allows you to instantiate these data flow graphs. The concept is static data flow. Obviously, the devices are finite, so at some point you run out of arithmetic space, you run out of on-chip memory, then you have to have feedback loops. There are some approaches, and this is the more advanced part of the talk or tutorial or methodology that we have, but there are solutions for that. I may have some examples. Then, this graph that you described should be big, because here you are running at 100, 200 megahertz, and you try to compete with technology that runs a few gigahertz, which means you have to win at something. Doing one addition, better do not consider this technology. But when you want to do thousands of them on a massive amount of data, then maybe this pays, because I can have these thousands all in flight running at different partial results, which means at each clock cycle, systologically, I will be moving my data farther and farther through this mass production data pipeline. And then, of course, this has to be supported by some tools. As I said, the streaming variables are the native data type. There is some exception. Sometimes I would like to have coefficients that I expose as scalars to the CPU, which means I can call this hardware accelerator with certain values for the coefficients, and being, I don't know, FIR filter, for instance, and then on the next call, I can call it with different coefficients. For that, I need the scalars. And then the memory where you place your data is just distinguished in two levels. You can force your data in the fast memory or place it in the large memory. Obviously, fast memory is beneficial, but it's, of course, limited, as in any computing technology. And when your data does not fit into the on-chip memory, then you have no other choice but put it in the high bandwidth L memory that we have. And then just an example. Floating, right, you can optimize on many different dimensions. Also, this is an example of the arithmetic dimensions, right? We said we can customize the data type and the size, but we can go even more, how I can say, in more depth. We can implement more interesting things. And just as an example, to break this holy belief that designers and even domain experts and scientists have in floating point, I have this example. And this example you can try on your computer. And this example shows you that floating point, that everybody thinks this is the golden standard of numerics and computation. So if you do double precision floating point, then you are done. It's not even associative. If you do these three operations with putting the brackets differently, you get a 20% deviation, which means, and indeed, understanding numerics, it is probably very important. And this technology and this way of programming accelerators allows you to go to that level and do things even as I'm showing here. You can split your arithmetic operation in smaller pieces and then use a redundancy to do the operations like we have seen that in the example of conditional execution in space. And then depending on what your lower nibble will produce, you just pick the one of the two results that are associated with carry between the two subarrays or no carry available. All of this you can do. So the methodology typically goes like that. We accelerate very often existing applications that are in development for a very long time. And you have to do a lot of thinking. You have to do a lot of understanding. Remember, that's why I put the slide citing Dan Slotnick earlier in the presentation. You have to identify the code that is really data dominated, and then do a system architecture, move not only the code, but also the data that this specific code works on the data side of your system. And then, once you have done this performance modeling, thinking about the numerics and the data management in your system, you can just write your code. Writing the code is easy. Integration, simulation, we do as an integral part of the tool chain. So in that respect, everything you just have available, all the I/O and the modules are there. They provide you streaming interfaces. You just define this DataFlow Engine variable, and then you know that as long as you define the type and the size, there will be a sequence of this element of the same type and the same size that will be provided to you compute kernel. Then this graph here, so you do the simulation on a high level. It's compiled a C-level simulator that is arithmetic level and cycle level accurate. And once you are happy with what you have been writing, you can do debugging, obviously. You can even use breakpoints, and breakpoints in DataFlow graph is a little bit more complicated, but there is support for that. You start the synthesis process. This is very painful because, as I told you earlier, we picked the largest FPGA that is on the market, which means there are thousands of arithmetic operations that have to be scheduled, placed, and connected. And we would like to fill it with useful computation up to the limit, right? Up to the 100%. And the tools that the vendors provide sometimes take 24 hours to produce the configuration. So that's why we have the simulator. You do a lot of simulation, and you do this once in a month or once in a few weeks. Because if this is part of your design process, you cannot have a compiler that takes 24 hours before it produces the result, right? So this is the painful part. Conceptually, we use Java, right? The company started 14 years ago. There was no Scala. Scala could be maybe a better example or better high-level language to pick. Unfortunately, Scala was not existing back then. Java is what is used. And for the same reason, a lot of Java programmers can be found easily. Can they all be trained to think in space, to think in a system level the way Dan Slotnick was pitching? More difficult, unfortunately. Now, you write your Java code, but this is not what you execute. You run the Java code once, and it generates your data flow graph. Once the data flow graph is generated, then everything happens on that intermediate level. The Java code is gone. So there is a clear decoupling between compile time and runtime. The Java code exists at compile time. You run your Java program, you generate the graph. Java code gone, doesn't exist. So integers you can use here, but once you have been generating the graph, they became invariant. They became hardwired constants that are linked directly to one or another input of some of the arithmetic operations in your graph. And to do that, you have to basically have an application where you extract the part that you want to accelerate. You write a kernel, right? We have the concept of kernels that actually implements the graph. And there is a manager. Manager is the wrapper around with the I/O interfaces that provide these streams of data and handle, obviously, the streams of data that the kernel produces. And all of this is integrated in Linux. There is a OS and a runtime library extension that allows you to do exactly that. Take the code in whatever high-level language, rewrite some of the pieces, then link it with the rest of your system and execute. So basically, high-level your application code, the kernel code, the manager code in the middle with the links where the streams come out, and that's what you have to do. I'm going to skip this example. I will provide the slides, obviously, for you convenience, but this is all integrated in an Eclipse environment where you can also visualize the graph. So you run the code, right? You actually compile, the graph can be visualized, and you can click on any node of the graph and see which line of code produce that specific graph. There are a lot of examples, so the programming is actually not difficult. You can go through the slides, and there are many slides. I knew that I cannot cover them in 20 minutes. There is, however, a couple of interesting things. For instance, very often in scientific code, we have the loop iterator also part of the arithmetic operation that happens in the loop body. Now, we said we unroll all these loops, right? So when we write something in the streaming data flow, the for loop disappears. That's why we override the for loop to generate hardware. So we unroll loops in space. But these are details, as I said, shown in the previous examples. Now, here I have a second stream. Implementing it as a second stream is, of course, a possibility, but it's a very inefficient implementation. So, which means I will use some of my I/O bandwidth to stream a very boring stream that will have values 0, 1, 2, 3, 4, 5, 6, 7, and minus 1. Very boring. For that one, we provide the method generate simple counter that will make a hardware structure that will generate this sequence of data values on the surface of the chip. And we have, of course, a primitive that generates even random number sequences. So this is just a good and interesting example. You can chain counters to resolve, right, nested loops. You can have lookup tables. And this is a simple example how you can write a sinus function evaluator of, 4096 functional value, right? You discretize the domain in 4096 segments. And then each of the values is a single precision floating point. So the only thing here, what I'm doing here during runtime is looking up in the table the right result. And then I'm done. For more complicated behavior, we have another method, the offset method, where I can have a relative offset from the data elements in my stream. And this is the good example of the moving average kernel, when I can have the previous and the next element. And this is how they're shown on the graph. And again, I can have flexible data site, floating point of 24 bits, 7-bit exponent, 17-bit Mantisson. Okay, I can do it. Then the arithmetic operations will happen on 24 bits. All the data paths here will be only 24 bits. They're not going to be 32 or 64 or 16. They will be exactly 24 bits. This part here generates, right, the arithmetic operations and connects them together. And of course, I can lay out my data in space. And typically offsets that we use in practical applications, they can be up to tens of thousands of offset stages. Unrolling in space is shown here with resolving dependency. There is tight control also on the style of arithmetic generation. You can use optimization factors to directly control the pipeline depth of a certain part of your graph, but these are more advanced things. Once you're done, of course, you call these external tools, and this is what makes the approach very interesting, because the backend is completely transparent to the designer. You do not care if we decided to put a Xilinx chip or Altera chip there on the surface. It is just up to the level of the data flow graph that you have to think and understand. And to help you with that, there are some profiling views where you can see your MaxJ code, and you see the utilization of the different instructions that you wrote from the basic utilities that this chip provides. You do not have to become an expert in what is block run, what is lookup table, what is flip-flop. You just have to know that they go between 0 and 100%. Once you're at 100%, then you have to do something. But with this view, you can find which line of code used most of these resources and do something on your code so that when you regenerate the graph, you may be able to put more compute on the surface of the chip, because that's the idea. You can even look at the latency. You can visualize the critical path. This is very important for low latency network applications. And the idea is to be able to build complex graphs like that. I'm done, I know. 0 minutes, I know. I'm pretty much aware of that. So, I'm going to say only one thing. We deployed just a system. Typically in the history of the company, we are building highly customized computers. So as I said, the ultimate custom supercomputers for a specific company with a hard problem that they cannot solve using parallel systems. But we are very happy that we were one of the hardware vendors in the praise procurement process, and we just last month deployed a system at the Jülich Supercomputing Center, which is one of the largest in Europe, and they will be using it. It's a very small pilot system with 8 of our latest generation cards compatible with the Amazon, so they would like to run small-scale simulations on that system and maybe large-scale simulations on Amazon Cloud. But now we are entering the general purpose high-performance computing domain. So this is interesting because there are a lot of challenges, so a lot of opportunities for collaboration. And here I want to say we're not alone, because 14 years ago everybody was thinking Maxeler is a crazy company. Now, and Xilinx and Amazon and Microsoft and Baidu and IBM and Xilinx, they have this super vessel, FPGA-based clouds. Everybody is there. Now, certainly people start paying attention. What can I say? We are a little bit ahead of the rest, but we are not there. We are still improving our technology. Sorry, questions?